Hello everyone, welcome to the first homologous series family in the organic chemistry. I believe that in the past, the previous topic, you have already learned about intro to organic chem. So the first topic in the whole series, the first family is actually hydrocarbon in particular aspect of the alkanes. So in this chapter, we're going to learn more about the alkanes. For this lecture itself, what we're going to do is that we're going to study the structures of the alkane, the structures of the cycloalkanes, the nomenclature of alkanes, how to name them, uh, isomerism, as well as the properties of alkanes. Before we delve into the chemistry of the alkanes, let's take a look at some of the common uses of alkanes. So the first one that you might be familiar with is actually an anti-corrosive agent. So you might be asking me, hey, what is an anti-corrosive agent? So an anti-corrosive agent is actually a chemical compound added to a liquid or a gas to decrease or the corrosion rate of the metal that will come in contact with the fluid. So basically is to prevent it from corrosion. So it can come in the form of an aerosol or it can come in the form of a liquid. The next one that is more close to heart is the whereby your propane and your butane can be used as a liquefied gas for cooking. So you might be wondering how does it look like? It's something like this. Okay, I believe this one is the one that you use during your steamboat. Okay, during a steamboat, I think some of your parents or your grandparents, okay, instead of using the electric kind, they will still be using this kind whereby they have to change the canister whenever there's no more guests. So usually during the Chinese New Year, if your family is eating steamboat, probably your grandmother or your mother or your parents will buy some to stand by. Yeah, so that is the one that is used for cooking. So this is a quick summary of what the importance of alkanes and how some of them are being used. Okay, so like I have alkanes used in plastic. They're used to make nylon plastics. Used in fuel. Okay, so used in wax. Okay, there are also some that is cycloalkanes, as you can read from here. Moving on, we are going to talk about the hydrocarbons of in general before we zoom into alkanes. So to show you this chart, you will see that hydrocarbon is actually divided into two. One is the family of the saturated hydrocarbon, namely the alkanes, and then there's the unsaturated hydrocarbon. If you see the difference between the saturated hydrocarbons and the unsaturated hydrocarbons, is actually the bonds. You notice that the alkenes and the alkynes actually have a double bond or a triple bond here. Okay, whereas alkanes, you can see that they are single bonds. So to explain the structure of alkanes a little bit further, alkanes are actually saturated hydrocarbons that contains either the carbon atoms, which are sp3 hybridized, or sp3 hybridized and tetrahedrally bonded to either the hydrogen atoms or another carbon atoms. So they are mainly single bonds. And you can see from this 3D image here, whereby the gray color one is the carbon, and then the yellow, green, blue, and pink is actually either hydrogen or another carbon atom. So the general formula of alkanes, I believe you have learned this in your O levels. It's CnH2n plus 2, whereby I have a series of different alkanes here to show you. You also notice that as my carbon atom increases, okay, the physical state at 25 degrees Celsius and 1 bar also changes from a gas to a liquid to a solid. You can also see that if I have C18, I have C20, it is actually a solid. Next, if we go on to the structure of cycloalkane, cyclo means actually cyclic hydrocarbon, in which they form a closed ring structure. So some examples of your cycloalkanes are this. You will have your 3 carbon, 4 carbon, 5 carbon, 6 carbon. Okay, so these are some examples of the cycloalkane. You will also notice that there is actually a little bit of difference in terms of their molecular formula. Okay, so you will notice that it is a little bit different. Cycloalkanes are isomeric to alkenes, okay, but they behave like an alkane. So why do we say that they are isomeric to alkenes? Because they actually have the general formula of CnH2n. Okay, but in terms of the saturation, they are actually saturated compound. That's why chemically they behave more like an alkane. Showing you an example, not say example, sorry, but a 3D model of your cyclopropane. So you can see that there's 3 carbon there, the blue, the black, and the red. Okay, so they are actually in a closed ring structure. Another view of it, you can see the triangle there, okay, between the 3 carbons. So that's your cyclopropane. So cyclohexane, hexane is 6 carbon in a ring. It's a common structure that you will use in the organic series. So I show you a 3D version of it. How does it actually look like? So it's something like this. You can see the carbons are actually colored in terms of red, yellow, and blue. Moving on, let's do our checkpoint 1. In our checkpoint 1, we actually talk about naming, and we also talk about drawing, how to draw the structure itself. So give you 1 minute now. Can you please try to draw out the displayed formula for the following alkanes or cycloalkanes? So you have your 2,3-dimethylbutane as well as your methyl cyclohexane. So just very quickly do this. You can pause the video if you want to, and then you can continue after you have drawn it and check your answers. Okay, welcome back. Hope you have drawn your structure. So let's look at the first one. The first one is a 2,3-dimethylbutane. So if I look at it this way, butane, I look at the longest unbranched chain. So the longest unbranched chain in this case is the butane. So given that it is the butane, the longest unbranched chain would be this. Okay, so being the longest unbranched chain, it's 4 carbon. Then I will have at the second carbon and the third carbon, I will have a methyl group. So this methyl means it's a methyl group lah. Where is it? It is at position 2 and position 3. So at position 2, at position 3, I will have one of each, which is this and this. So that is how you have your 2,3-dimethyl butane. Next, when I look at my methyl cyclohexane, my longest unbranched chain, or the structure that I need to draw first is actually my, oops, wrong. It's actually my why like that? Oops, sorry. Okay, it's actually my cyclohexane. So I will draw my cyclohexane first. So this is my cyclohexane. Okay, this is my cyclohexane. And then methyl cyclohexane, that means on one of the carbon, you draw your methyl group. Okay, and given the fact that in this question they ask for the split formula, the split formula means that you have to draw everything out. Okay, you have to show all the bonds. So that is why you can see that each carbon here, although usually in our structure we will just draw it like that. Okay, oops, not nice. In our structure we'll draw it this way. But then when they ask for the split formula, means that you have to show all the bonds. So that's why I will show all the bonds. So that is my checkpoint 1. Next, let's move on to isomerism. Now, in isomerism, there is quite a few types of isomerism that you learn. So, in alkane situation, we will be able to exhibit the structural isomerism, or sometimes they call it the constitutional isomerism, or the enantiomerism. Enantiomerism is the one whereby you have your chiral carbon. So if you need more help on this isomerism, please refer to your Introduction to Organic Chem lecture notes again to revise the concept of the isomerism.
You will now write the structural formula and names of all the constitutional isomers with the same molecular formula, C6H14. Now, since the question asks for structural formula, you have a choice of using skeletal formula, condensed formula, or displayed formula in your answer. My personal preference is to draw using a skeletal formula as it is faster and easier to check for repetition. Now please pause the video now to try this checkpoint. Let's now try and go through the answers. Since the molecular formula fits into the general formula of alkane CnH2n plus 2, we know that we should be drawing only alkanes. Of course, one is a straight chain and the rest are going to be branch alkanes. Now, you are advised to draw the alkanes systematically to avoid drawing the same alkane in a different orientation. So we begin with a straight chain, which is a 6 carbon length. So this is an hexane. So you can also choose to draw the show it in a form of condensed formula, okay, which is this in the middle. All right. Now, for condensed formula, you will notice that there's a lot of repeating unit of CH2, CH2, 4 of them. Therefore, you can also choose to write it in this form with a bracket CH2, 4 of them. Okay, this is also accepted as your condensed formula. So use the bracket and number 4 because we have repeating units of CH2. Once we have our straight chain, we can now try and draw for a 5 carbon length parent chain with a methyl group as your branch. So we could have the branch on the second carbon and the third carbon. Now take note, when you are putting this in the fourth carbon, this is actually a repetition. Okay, so this structure that we have here is actually the same as this one that we have, okay, with the methyl group on the second carbon. So to name this, this is a 5 carbon chain, parent chain. So the root name has to be pent. Okay, so we have pentane with a methyl group on the second carbon. In terms of the condensed formula, note that the branch, methyl group side branch, you have to put it in a bracket to show that this is actually attached to the second carbon over here. Now you can also choose to write condense further the repeating unit of CH2. So the two repeating unit can be condensed into the CH2 CH bracket 2 over here. The third compound is 3-methylpentane. Remember, we are still looking at a 5 carbon parent chain with a methyl group on the third carbon. So the condensed formula shows the methyl group in a bracket, and this means that the methyl group is attached to this carbon just before it. We will now look at the 4-carbon parent chain. So the parent chain will have the root name of bute. Okay, so this is a butane with 2 alkyl group. Okay, so 1 methyl group on the second carbon and another methyl group on the third carbon, right? So you can choose to put the 2 methyl group separate on separate carbon, or you can put them together attached to the same carbon. So this will give rise to 2 different structure. Now, if you try to put the 2 methyl group on the next carbon, note that this is a repetition. So these 2 structure, they are actually the same. It is just drawn in a different orientation. In terms of the naming, because I have 2 methyl group, so this is on second carbon and the third carbon. Therefore, if you look at the name, this is 2,3-dimethylbutane. Okay, di for 2 methyl on position 2 and 3 of the parent chain. For the condensed formula, you will notice that there's 2 CH3 in a bracket. So this indicates the 2 methyl side chain. So the first methyl group here is bonded to this carbon. Okay, this is the second carbon. The second methyl group that appear is supposed to be bonded to the third carbon over here, right? So this is my third carbon. For the last structure, when my methyl groups are on the bonded to the same carbon, I can condense this by showing the bracket CH3, and this number subscript 2 indicates that there are 2 methyl group, and they are all bonded to this carbon over here, which is my second carbon. Name-wise, this will be named as 2,2-dimethylbutane. So this means the methyl group 2 of them are both on the second carbon of parent chain.
Moving on to checkpoint 3. So in this checkpoint, you are asked to draw the structural formula of the simplest alkane which can exhibit enantiomerism. In order for me to exhibit enantiomerism, I understand that there must be a chiral carbon. So you have to think of a way such that you have based on the alkane, they never tell you what is the alkane, so you have to think about it. Which one is it that can allows me to exhibit enantiomerism? So give you about 2 minutes to think about it. What is it that you want to draw for part A? And then for part B, you have to draw both of the enantiomers that you have identified in A. So give you 2 minutes to do it, and then you can come back to play the video after you are done with drawing the formula, the structural formula. Welcome back. Let's look at the structural formula of the simplest alkane. That means the smallest number of carbon that you need, okay, that will result in an alkane that can exhibit enantiomerism. So the one that we can think of is whereby the 4 different groups, the substituent has to be different. So we will have this. So if I'm going to draw this out for you, right, how would it look like? It will look like this. You have your carbon on top, one carbon with a H, which is this. This is the carbon. And then one of the carbon, it will be bonded to a CH3. Maybe I draw it. I follow this. I will be bonded to a CH2, CH2, CH3, and I will be bonded to a CH3, CH2, and I'll be bonded to a CH3. So this is the structure that you will see when you draw out based on what you see on screen. So if I'm going to name this, I'm going to name it based on the longest unbranched chain, right? So in this case, my longest unbranched chain is 1, 2, oops, there will be 1, 2, 3, 4, 5, 6. Correct? So my longest unbranched chain is a hexane. Yeah, it's a hexane. Okay, then on the second carbon, no, on the third carbon, sorry, on the third carbon, I actually have a methyl. So it's 3-methyl hexane. Okay, so this one will be named as 3-methyl hexane. Next, you are asked to draw both the enantiomerism. So based on this structure, you know that you actually have a chiral carbon here. So if you have a chiral carbon here, you are supposed to draw it out. So I will draw it out. When you draw your enantiomerism, you will need to draw it in a 3D manner. That means to say you will need to show your dash and your wedge, the bow line and the dash line. Then the mirror image of it is this is what you see. Okay, so my suggestion to you is to put the most complicated one at the top. So in this case, the most complicated one is actually your CH2, CH3. So I would recommend putting this at the top, and the rest you can just put it in. And please do not flip your CH2, CH3 because it's not allowed. So just draw it as per it is, like this. If I'm going to show you in terms of the 3D molecule, it will be something like this, whereby it is non-superimposable mirror images of each other. Okay? Moving on, let's talk about enantiomerism in cycloalkanes. So like mentioned, the cyclic compounds can also exhibit enantiomerism if they have a chiral center. So if I'm going to look at this compound here, which is called the 3-bromocyclohexanol, it is called a hexanol because there is a OH group here. Okay, so 3-bromo is because this one is seen as carbon 1, carbon 2, carbon 3. So 3-bromocyclohexanol exhibit enantiomerism due to the presence of two chiral center. So now I'm going to teach you how to look at the chiral, how to determine whether is there a chiral center. So let's take a look at the compound here. So this one is the carbon. Let's see how many different substituents does this carbon has. So I have one H, one OH, one H, one of this carbon here, and one of this carbon here, correct? So these four substituents are the ones that is bonded to the carbon. So then in that case, I move on again. I'm going to look at it further. So this carbon is actually here. The whole thing here is actually bonded to this carbon, right? The next neighboring carbon. And comparing next to it is this one also have a Br. This carbon here has a Br. So can you see that they are actually different? One, the next carbon is actually the one with a CH, whereas for this carbon, it is one with a CBr. So this carbon and this carbon is different. So because of that, we can say that this one, okay, this thing here and this thing here is different. So this the carbon in the brown actually has four different substituents. And let's look at the one in green, the carbon in green. So same thing, I also circle out the four different substituents that I have. So I will have a H, I will have a Br, I will have this carbon here, and then I put this carbon here again. So the two carbons at this moment, they look the same, right? So I go on to the next carbon. When I go on to the next carbon, you will notice that, hey, the next carbon is different from the one that I have. This carbon is different from this carbon. So then I can say this substituent in blue is different from this in green. So I say that this one has four different substituents and they are considered a chiral carbon. So because of that, I can make a conclusion that I actually have two chiral centers in this cycloalkane. Now, this is not good enough because this is a 2D. In terms of enantiomerism, I need it to be 3D, right? So if I need it into 3D, that means I need to draw the bow line and the dash line. So which means to say I need to draw it out. And I need to draw their mirror image. So this is the mirror image. So for this one, what I suggest you concentrate on one first. Okay, you draw the bow and the dash. And then the same thing after you do for the first one, then you do for the second one, then you will not be so confused. Then you draw the bow and the dash. Okay, so that is your chiral centers in a cycloalkane. Moving on, let's look at a particular compound. Please identify the six chiral centers. So I give you a clue, there are six of them. So please um, identify the six of them. Give you 2 minutes to do it. This is usually an MCQ question. Okay, welcome back. Let's find out the six chiral centers. The first one is here. How do I know? Okay, you can see that this carbon actually has 1, 2, 3. This part is different from this part, 4. So this is the first chiral center. The next one, where should I look at? Okay, when I'm looking at a chiral center in this kind of complicated molecule, I will usually target the complicated parts. Okay, I will target the complicated parts. So let's take a look at the next one. Where other possibility can it be? The next one is actually here. So if I look at the next one, so let's move on. So where is the 4 different substituent? I will have a H here. No, this one don't have H, sorry. It's at the bottom, don't have H here. So I'll have 1, 2, 3, and 4. So I will have the second chiral center. Moving on, there's 6 of it, right? So I found 2. Where's the third one? Same thing like always, target the complicated sites. So where are the complicated sites? Here. Okay, so if I look at this again, let's try. Look at the next one. So same thing here. I have 1, I have 2, I have 3, and I have 4. So can you see that the carbon next to it is actually different? So that's why I have 4 different substituents. Now I have looked for how many already? I have found 3 already, right? So I need another 3. So where is the fourth one? The fourth one is actually at here. Why is it so? Because if you look at it, same thing. I have 1, 2, 3, and the last one is actually your H, which is 4. And then the fifth one, where's the fifth one? Oh, a bit messy, yeah. Let me erase off. The fifth one is actually here. So how should I go about doing it? Same thing. I try to look for the 4 different substituents. So I have 1 here, the big part, the big thing here, 1, and then I have the carbon 2, 3, and the last one is actually your H. Okay, so I have looked for 1, 2, 3, 4, 5 already, right? So the last one is actually here. So using the same logic, you can actually find out the different substituent on that. Okay, my whole picture very messy already. Now, so what I want to tell you is that first thing, if you are looking for a chiral center, usually I would advise to target the most complicated site because that is the higher tendency that you're going to get for different substituent. Okay, I won't be targeting things like this. This one I'm not interested because this one very obviously this one is a H, this one is a H, right? So both of them are H's, then I won't target already. Why would I want to look at it? It's not a chiral center. Another thing that you can ignore, okay, is carbons with double bonds. Because if I have carbons with double bonds, they actually they will not have 4 different substituents. So because if they don't have 4 different substituents, then I can forget about it already. So like for example, this carbon, I won't even look at it. This carbon, I won't even look at it. I won't even look at it because there is a CC double bond there. I won't even look at this carbon because there is a CC double bond. Not CC, sorry, C double bond O. And I won't even look at this because there is a C double bond O there. Okay, so there are some carbons that you can ignore. One look of it you can ignore. And then there are some carbons which you want to take a closer look to see if there are 4 different substituents. So basically that is the technique how you can actually find out or identify the chiral centers in a molecule. Moving on, we have talked largely about the structures, we have talked about the nomenclature, we have talked about the isomerism. Now, I would like to move on to the properties of alkanes. Okay, so for the properties of alkanes, there are a few, like you can see in your notes on page 7. There is actually the melting and boiling point, you have the density, you have the solubility, you have the chemical properties. Okay, so we will look at it individually to understand it better. So the first one that we look at is melting point, melting and boiling point. So whenever we are talking about melting and boiling point, what are we looking at? We are looking at the intermolecular forces of attraction. Okay, and you notice if you refer back to your page 3 of your lecture notes, you will notice that the boiling point and the melting point actually increases as the number of carbon atom increases. So then the question is why? Why is it so? Okay, so the reason for it is because of the strength of the IDID forces of attraction, or you call it the instantaneous dipole-induced dipole. So because alkanes, they are all simple covalent structures, so with they are non-polar, so they actually have IDID forces of attraction between the molecules. So as the number of carbon atoms increases, your number of electrons in the molecules also increases. And because the number of molecules increases, you actually need more energy to overcome them. So when you need more energy, naturally the IDID forces of interaction would increase. Next, let's look at density. So if you look at the density, same thing here, you would also notice that the density actually increases as my number of carbon atom increases. So we will also like to know why. Okay, like to find out the reason. Okay, let's look at the next property, which is the density. So alkanes are less dense compared to water, and the reason for it is actually because of the type of intermolecular forces of attraction that exists between the alkane molecules compared to the IMF between the water molecules. So you notice that per unit volume, okay, there is actually less alkane molecules compared to the water molecules. And the next thing that we see is that alkanes actually show an increase in density when the number of carbon atoms increases from the table that you see previously. So the reason for this is because as the number of carbon atom increases, the molar mass actually increase, right? So the density will increase as the increase in the molar mass is more than the increase in the volume. So that also explains why your alkane shows an increase in density down the group. Okay, next we're going to talk about the solubility of alkanes. Alkanes are insoluble in water. I think all of you know why. Okay, because it's actually the different types of IMF that exist between the alkanes and between the water molecules. So in this picture here, I think you can't see very clearly. Let's see if I can show you. Okay, you will notice that when I pour in the alkane, you will actually see that there is actually two layers forming. Here, yeah, you can see. Okay, the layer on top is the alkane, and then the water is actually at the bottom. So they actually do not mix when you pour them in the same beaker. Okay, so let's take a look at the reason as to why the two layers do not mix. So if you can see it this way, okay, I can actually have my solute and my solvent, right? So when I have my solute and my solvent, this is similar to what you have learned in chem bonding. So step 1 and step 2 are actually endothermic because you actually need the energy, okay, to separate, okay, the particles in the solute as well as the particles in the solvent. Okay, step 3 will be the one that is exo because attraction is being formed. Okay, so when the attraction is being formed between the solvent and the solute, so overall you can have an enthalpy change of solution whereby you actually have the all the steps, you add them all together and you see whether is it positive or negative. So as to say, okay, so if okay if I have, okay, if I have a substance dissolving, Okay, that means to say the energy release, okay, is actually enough, okay, to compensate for the energy needed, okay, to overcome the bonds, the attractions between the solutes and the solvents, okay. Whereas whereas if not, then it cannot lor. If it's not enough to compensate, then cannot. Okay, so that is the idea between the solubility, why alkanes are generally insoluble. Because if you look at alkanes itself, right, uh, the energy needed to overcome the strong hydrogen bonds between the water molecules, right, they actually need more energy to overcome the strong hydrogen bonds than the energy that is released from the formation, the interaction that is formed between the alkane and the water molecules, because alkanes are generally non-polar, and then water molecules are polar. So alkanes non-polar, water molecules polar, they cannot form favorable interaction. So they will form the weaker ID forces of attraction. So because of this, then the energy release is not enough to compensate for the energy needed to overcome the hydrogen bonds between the water molecules. That's why ultimately your alkanes and your water, if you look at the just now that video, the hexane and the water, they actually form two layers. Next, let's look at the chemical properties of alkanes. So alkanes itself are non-polar because they only have the C and the H bond. So the C and the H bond are non-polar. So they are unreactive towards polar reagents or polar solvents. Okay, one thing to note also that the CC bond and the CH bond is very strong. So because it is very strong, I actually need a lot of energy to overcome these strong bonds in order for my reaction to occur. So that is why if you notice for reactions of alkanes, you actually need heating, or you need UV light, okay, or you need sunlight, okay, in order for the reaction to take place. We are going to look at it in greater details in our next lecture. So in summary for today's lecture, we talk about the structure of alkanes, we talk about the structure of cycloalkanes, we talk about the nomenclature of alkanes, and finally, we also talk about the enantiomerism of the chiral center. I teach you how to find the chiral centers. And also, finally, we also talk about the physical and the chemical properties of alkenes. So that is largely for this lecture. Thank you, everybody. See you again in lecture 2.